Hi, and thank you for joining today's presentation entitled PMO Guidelines, Creating Pasteurized Equivalent Water with Ultraviolet Disinfection. So our agenda for today will be an introduction of our speakers, followed by a brief introduction of Aquionics, the sponsor of today's presentation. We'll then speak a little bit about UV basics to make sure everybody's on the same page with terminology. At that point, we'll cover the requirements of UV in the PMO, and then move to process and site considerations, and finally wrap up with equipment options that meet the PMO. So an introduction of our speakers. So my name is Ken Kirshner. I am the Aquionics Regional Director for the Americas. Following me will be Brian Wachowski. Brian is an Aquionics Regional Manager. After Brian, you'll hear from our guest speaker, Stan Pritchard. Stan is the Sales Area General Manager for Rotem, and Rotem is a leader in sanitary process products, operations, integration, and repair services. And then finally, Dan Schaefer will finish our presentation, and Dan is also an Aquionics Regional Manager. So a little bit about the sponsor of today's presentation, Aquionics. Aquionics is owned by Halma. Halma is a company based in the UK. They're on the London Stock Exchange as part of the FTSE 250. Halma have over 4,000 employees working for 50-plus companies around the world. The Halma businesses are divided up into 4 sectors, which are shown here on this slide. The environmental analysis sector is where Aquionics falls in, and we are part of a UV group consisting of 3 UV companies. So first there's Aquionics. Aquionics was established in 1983 in Erlanger, Kentucky, which is right outside of Cincinnati, Ohio. Aquionics is responsible for the sale of industrial, municipal, and commercial systems in the Americas, so North and South America. The second UV company is Hanovia. Hanovia was founded in 1924, and they're based in Slough in the United Kingdom. Hanovia are responsible for the sale of industrial and commercial products in the rest of the world, excluding the Americas. And finally, the third company that makes up the UV group is Burson. Burson was founded in 1972. They're located in Eindhoven, Holland, which is right outside of Amsterdam. And they're responsible for the sale of municipal products throughout the world, except for the Americas. So Aquionics sell into multiple markets. Those include the swimming pool market, pharmaceutical, food and beverage, marine, and specialty applications. And today's presentation falls under the food and beverage market, specifically our third-party validated product, which is called the PureLine PQ. So now let's talk a little bit about UV basics, just to make sure everybody's on the same page with some terminology. So the first thing is what is UVC? So UVC is produced, for this application we'll be speaking about using either a mercury or xenon gas lamp. The UVC energy passes through the cell wall of the bacteria or virus. Once that happens, the DNA or proteins or RNA of that bacteria absorb that UVC energy. And what this causes is the DNA strands to become attached, leaving the organism unable to replicate. This is called deactivation of an organism. As you can see in the lower left-hand side, the optimal wavelength for DNA absorption is 264 nanometers. And this falls within the UVC light spectrum. So on the right-hand side, you'll see a light spectrum, and from 200 to 280 nanometers is UVC energy. After that, you've got visible light and infrared, and while not shown, on the other side of the chart, you would have X-rays. So a little bit about different lamp technologies that are available. So there are 2 lamp technologies, low pressure and medium pressure lamps. A low pressure lamp is considered monochromatic, and you'll see in the top right corner a chart that shows the output of a low pressure lamp. It has a single output at 254 nanometers. Low pressure lamps are typically longer lamps and they require more lamps to treat the same amount of flow as a medium pressure lamp. A medium pressure lamp is polychromatic, and you'll see the chart in the bottom left for a polychromatic lamp. It has multiple wavelengths across the light spectrum. This enables a medium pressure lamp to penetrate multiple aspects of an organism, including the proteins, DNA, and RNA. Medium pressure lamps tend to be smaller and require less than low pressure lamps, meaning that you have a smaller footprint and less equipment. There is a right place for each technology. It all depends on your application. One is not necessarily better than the other. It just depends on what your site needs and what's right for your technology. So let's talk about the different pieces that make up a UV system. So there are two major components that make up a UV system. One is the UV chamber, and the other is the electrical control panel. A UV chamber consists of a stainless steel chamber that houses the UV lamps and quartz sleeves. The quartz sleeves are there to protect the lamps from the liquid that's flowing through the chamber. Some other typical components that make up a UV chamber would include an automatic wiping system to keep the quartz sleeves clean, a temperature sensor, and a UV intensity monitor. The intensity monitor is there to measure the output of the lamps, the aging of the lamps, and any fouling that might be taking place on the quartz sleeves. The other component is the electrical control panel. The control panel typically has a screen that displays the operating parameters, the performance of the equipment, allows the site to program in any specific characteristics for that equipment. It would also have the lamp power supplies, an emergency stop, and customer contacts to take any control signals. I'm going to turn the presentation now over to Brian Wachowski, who's going to cover the requirements of UV in the PMO.
All right, thank you, Ken. So in regards to the UV in the PMO, this is a document, first of all, that those of you based in the dairy industry here in the U.S., you're probably quite familiar with the Pasteurized Milk Ordinance. Those outside of the U.S., this is basically the regulatory guidance document for dairy facilities here in the U.S. The FDA is the regulatory authority, and UV made its way into the Pasteurized Milk Ordinance in 2009. There are two sections that talk about UV as a technology and its uses within a dairy facility. One is in Appendix D, which talks about continuous water disinfection, and the other one is in Appendix H, which talks about the creation of pasteurized equivalent water. So maybe firstly, since we are talking about equivalence between UV and pasteurization, I thought it would make sense for us to maybe take a minute to look at the performance differences between the two types of technologies. Because of course these technologies are very different. One is working through extreme temperatures and time, and the other, as Ken mentioned, essentially through scrambling the DNA of organisms. As many of you know, of course, HTST pasteurization is well known to provide a 5-log reduction of organisms. And when it comes to utilization of pasteurized water or pasteurized equivalent water in the dairy, this is important for any water used where it's going to come into contact with final pasteurized product. Just in case there are any issues with the city water or any of your initial water sources, it's important to treat that water to pasteurization or UV to the standard to ensure that you do not accidentally contaminate your product. But looking at pasteurization as a 5-log reduction of organisms, what I thought it would be interesting is to maybe take a look at some of the common organisms that are of concern in a dairy and look at what their UV dose responses are. In particular, for those of you in the quality lab, you're probably quite familiar with running total plate count test or total aerobic count, coliform, E. coli, maybe you're even running listeria, of course, after the bluebell incident. So what I wanted to do is highlight in particular something like E. coli, which does have pathogenic strains and is worth maybe taking a closer look at. So this graph here on the left of the slide, the straight line, bold line, is E. coli's dose response. So what you see along the bottom is the UV dose delivered, and the log inactivation along the vertical axis. The dotted line, by the way, is another organism known as a bacillus, which again is a possible contaminant in dairies as well. But the point here is to show that when you're looking at doses as low as 15 to 20 millijoules, you're able to reach this 5 to 6 log reduction, which is equivalent to pasteurization. Also on the table on the right, again, these are some organisms that are commonly found in dairies. These in particular do have some heat resistance, so some thermotolerance, so they are been known to survive pasteurization. And not only that, many of these organisms actually do like to grow in cold temperatures as well, so they are kind of the trouble organisms of concern. So you can see here organisms, again, like Listeria, Clostridium, Streptococcus, Pseudomonas, etc. All of these are highly susceptible to very low UV doses. So again, anything really in the range of 20 to 25 millijoules, you're able to achieve this 5 log reduction. So what I thought I would do is take a closer look at this Appendix 8, Section 9 that talks about utilization of UV for creating pasteurized equivalent water. In this section of the document, it's very brief. It's only 2 pages. And of course, that can be good and bad. There's not a lot of things that you need in order to comply. There's only 10 bullet points that we'll go through. But because it's so short and concise, it leaves a lot of these points up for interpretation. So depending on who your regulator is, the state agency, et cetera, they may want more documentation or have a different way to interpret this than another one. So what I'll try to do as I go through some of these is to maybe point out some potential questions that a regulator may have, since it's not very clear from the regulations what's required in some cases. So firstly, it talks about the performance of the UV system. Very specifically, you can see in Section A and B, both technologies are allowed for use for creating pasteurized equivalent water, and you can see the standard that they're utilizing is performance against adenovirus. What they want to see is a 4 log inactivation of adenovirus. So for many of you, I'm sure this probably is not an organism that you test for on a regular basis, but a lot of this information stemmed from the work that the US EPA did many years ago in the municipal drinking water regulation. What they found is that many of the organisms, like the ones we looked at in the previous slide, are highly susceptible to UV at very low doses. But some, particularly adenovirus, have greater sensitivity to UV than some of these other common microbes that are probably really more of a concern in your organization. And what they found was that the different technologies actually performed a little bit differently on adenovirus. So just another point of terminology, you can see when you look at the low pressure dose required for 4 log adenovirus, it says 186,000 microwatt seconds per centimeter squared. This would be the same as 186 millijoules per centimeter squared. So just the same, different unit of measurement, just another way to say it. Same thing with medium pressure, 120,000 microwatt seconds per centimeter squared. This is the same as 120 millijoules. And so that's the terminology we'll use throughout the rest of this presentation. So it's interesting to note that medium pressure does perform better than low pressure against this particular organisms and many others for the reason that Ken mentioned. Because of that polychromatic output, you're inactivating the organisms not just in the germicidal range, but also those higher wavelengths are disrupting proteins and enzymatic pathways, etc. So you're able to utilize a lower dose for the same level of performance. So as far as specifying the UV system that meets this, there are a lot of things that aren't mentioned in this first bullet point. A regulator may ask you, what can you provide or what can your UV manufacturer provide you to demonstrate that this UV equipment meets the performance requirements? Do they just require a letter from the UV manufacturer? Do they want to see that the system has been validated by a third party, an independent party, that's validated the performance? Do they want the system tested to any globally recognized protocol? For example, the US EPA has laid out some specific guidelines on how to challenge UV systems in their UV disinfection guidance manual. Maybe a regulator is aware of that and wants to see information along those lines. Also, as you can imagine, a UV system is going to perform differently depending on the piping coming into the system and the piping going out of the system. So for example, if you bolt elbow right at the inlet and an elbow right at the outlet of the system, that's probably not going to perform as well as a vessel that has a lot of straight line pipe before and after it. And again, a lot of this sort of testing would come out by a third party or an independent party that can analyze that information. None of that is mentioned in the PMO. So one regulator may look at this and simply ask for a very simple letter from the manufacturer stating that they meet the 4-log adenovirus claim. And others may want to see a UV system that's been third-party validated to US EPA UV disinfection guidance manual protocol with a piping configuration similar to how that system was tested during the validation process. And this is important to figure out up front, not just when comparing UV vendors, but of course this is going to affect the process if the piping configuration becomes part of the discussion. So the second bullet point talks about a flow or time delay mechanism. I'm going to allow Stan to discuss this more in his section since he's going to discuss process. But obviously you want to ensure that any water that moves past the UV system that's off spec doesn't make it further down into the process for actual use. The third point here talks about the system needs to be able to be cleaned frequently. So in other words, it needs to be able to be CIP'd. In addition, Ken talked about the importance of having an automatic wiper on the system to help clean the quart sleeves. An automatic wiper alone does not meet this particular bullet point, but it is nice to have because it does reduce the cleaning frequency required from CIP. The other thing to keep in mind regarding CIP is, quart sleeves around the UV lamps are highly susceptible to fouling and etching from very strong acids and very strong bases. So it's important to work with your UV manufacturer to understand your CIP timing, what chemicals are going to be used, and make sure it's not going to be a problem for the UV system. So the fourth point here talks about a flow control valve. So any UV system that is sized for a particular application is going to have basically a maximum flow and maximum water quality that it's going to be able to handle in order to treat to a 4-log adenovirus requirement. Again, this is important to work with your UV manufacturer to understand how close is this system sized to its max capacity, and how are you going to be able to control your flow to ensure you do not push more flow past the UV system than what it can handle. Bullet point 5 and 6 talk about the UV intensity sensor. So again, as Ken mentioned, this is a sensor that's mounted on the UV vessel. It's basically shining a light through the water, through the quart sleeve, to the UV lamp, and measuring the amount of output from that UV lamp. You can see in the 6th bullet point it talks about the need for 1 sensor per lamp, because obviously you would want to monitor each lamp to make sure that the intensity is given the amount necessary in order to provide the dose in order to meet the regulations. I would just suggest we've seen a few installations where there's not 1 sensor per lamp. Sometimes we've seen vessels where there's 1 sensor per vessel, or 1 sensor per 4 lamps, or something like that. Just be sure in order to meet this regulation, you are working with a system that has 1 sensor per UV lamp. The 7th point here talks about a different analyzer, a different sensor, and this is measuring the UV transmittance of the water. So this is a water quality sensor where the UV intensity sensor is basically a lamp intensity monitor, so it's a different device. So the UV transmittant analyzer is something that's placed upstream of the UV system for the same reason a flow meter is going to be upstream of the UV system in order to measure the water quality in real time. So this bolts right into the pipe, it shines light through the water, and it's measuring how much UV light passes through 1 centimeter of that water. So obviously very high purity and very clean water, you're going to have 98% or 99% of that UV light be able to go through it. But as that water quality declines and the UV transmittance declines, the UV controller that's gathering this information from the UVT analyzer is going to have time to ramp up power to compensate for reductions in water quality. So I wanted to note, particularly in this point, it's very important not just to have this UVT analyzer as part of the requirements for compliance, but also make sure that you have this far enough upstream ahead of the UV system so it's able to capture the signal from the analyzer and ramp up power accordingly in case you do have declines in water quality. Otherwise, you're going to have more diversions because you're not able to meet that 120 millijoule dose in the case of medium pressure. Bullet point 8 talks about a flow diversion valve, so Stan will talk about this a little bit more, but obviously any water that's deemed to be off-spec by the UV system, since it is monitoring in real time, it needs to be able to communicate with a diversion valve so it doesn't make it further into the process. Bullet point 9 basically talks about the equipment needs to be of sanitary and hygienic design. For what it's worth, there is no 3A standard for UV equipment, so something to keep in mind and work with your regulator is that you're going to need to work with your UV manufacturer to make sure they have adequate documentation to satisfy the regulator, since there is no standard along those lines. So the 10th bullet point is a pretty important one. So this one obviously is not just do we need to have the process right, but we need to monitor it. We need to be able to report in order to show compliance. So the parameters they want you to monitor and report on are flow from a flow meter, UVT from the UV transmittance analyzer, and dose from the UV controller. Specifically in Appendix H, Section 5, it lays out some very specific guidelines on what's required for electronic reporting of these particular parameters. We've seen some customers just capture the 4 to 20 milliamp signals for these different values and utilize a chart recorder, for example. But if you do want to comply with the electronic reporting requirements, this is something important to really challenge a UV manufacturer on, as frankly it wasn't something that was standard 5 or 10 years ago for us to comply with this. So many companies have developed software packages or open platforms so that you can better comply with this particular part of the regulation. So think about, how are we going to provide and print reports and give them over to the regulator? If you have a central plant automation system, will the UV system be able to communicate with it? Will they be compatible? Is there a separate laptop or device that you need to bring to the UV controller? How does it work? For us, and Dan will discuss this a little bit more, but this is why we partnered with Rockwell and Allen Bradley to develop an open platform that we felt would be more easily integrated at the dairies here in the U.S. And I'll allow Dan to talk about that a little bit later. But this is something to consider. So obviously it's not just about meeting the process requirements and performance requirements, but being able to monitor and report it as well. So I'd like to introduce our first polling question at this point before I turn it over to Stan. The question is, what roadblocks do you think exist at your facility or project for using UV in lieu of pasteurization? So it's either technical understanding of UV, B is confidence in UV, C is perception of price or maintenance, or D is if there is an other request. So I'll give you just a few seconds to review the question again, look through the answers, and we'd certainly appreciate your response. Okay, great. Thank you very much for that. I appreciate your responses there. I'll turn this over to Stan Pritchard to discuss the process aspect of things a little bit further.
Thanks, Brian. Ken has presented what UV does and how it can be used to deactivate bacteria and viruses, and Brian has just presented the guidelines for PMO for pasteurized equivalent water. I've been asked to review how this technology can be integrated into an operational facility and what needs to be considered in designing your system. So first, you need to define what the proposed use of the water being subjected to UV treatment will be used for. And even though we are primarily focused on pasteurized equivalent water today, there are many other uses for UV in dairy and food facilities, such as setting up a firewall for disinfecting all the water that comes into the facility, using UV to disinfect water after activated carbon beds, using to extend the life of RO filtration membranes, and of course, what we're focused on today, pasteurized equivalent water. So what are some of the areas to consider for your system? Are your users going to be continuous or intermittent? What is the max flow rate you'll need? And you may want to consider a storage tank for high use periods. The total flow anticipated during the day, and how does that vary throughout the week? And what are your incoming water conditions? As Brian has mentioned, UVT, flow, and pressure, really boiling down to water quality and availability. Where are you anticipating placing a unit? And without a buffer tank, diverted water at 250 gallons a minute and higher, drains can become an issue. So for pasteurized equivalent water, we need to control the flow. I'm sorry, we're going to go back a slide. Sorry, guys. We need to control our flow. We're required to monitor and control it. We need to handle divert control where timing can be critical. Some issues like will the system be skidded or site built? And local considerations as backflow requirements are a little different in different states, hydraulic issues for your specific system, and how to handle overheat issues, and of course, various regulatory considerations as well. As has been reviewed earlier, the PMO requires certain criteria and components. We're going to start with the first one is not really a required component, but we have found it's very useful, and that is a pressure reduction valve or flow limiting valve. It's typically needed to balance the system as you have many other users in a plant typically. And in the case of a flow limiting valve, this creates an additional safety for the system, as a flow limiting valve can prevent flow over the design capability through your system. Next would be a flow control valve. Simply stated, it controls the flow and ensures that the minimum dose for the water passing through the chamber has been subjected to 120 millijoules of energy. That's PMO requirement number 4. The UVT monitor. Water transmittance has a key impact on the flow and dose considerations. Again, PMO requirement 7. The magnetic flow meter is measuring the water flow through the chamber, and through an algorithm using flow and UVT feedback, control the light intensity. PMO requirement number 2. Next is the divert valve. Here's a little bit of a quandary because we must ensure that the reaction time of the valves and the distance from the unit are considered to ensure that no inadequately treated water gets into the system. That's PMO requirement number 8. The next is a provision for CIP, PMO requirement number 3, and also the wipers in the UV system extend the life between CIP, sample valves both pre and post UV for quality testing and assurance. And now, next slide here. There are some additional things that are required in certain areas and certain times, and I'll just start with those kind of briefly. The first is potentially a backflow preventer immediately before this system, a relief valve to take care of any hydraulic issues that we may have, a recycle or storage tank for diverted flow, really the storage tank is for balancing water usage, I should say. Any required pumps that we may need, and temperature monitoring the system to assure that enough fresh water during recycle is in the system to avoid overheating of the UV unit. Pressure gauges for setup and review. So the next slide really starts the review of the PNID. So this is how we would show a fairly simple continuous flow system, moving left to right. This is showing about 250 gallons a minute. We start with a CIP swing. Of course, that could be automated for if chosen, but right now we're just showing a swing connection. And then we start off with pressure indication coming out of the system. And then we're looking at our pressure reducing valve. And this one actually shows that flow limiting valve that I discussed as well. We then would go to a UV transmittance monitor prior to the UV system. And that's just measuring, as Brian has pointed out, the UVT on a real-time basis. Flow control. And again, we typically have pressure indication after our flow control. The magnetic flow meter with appropriate spacing to ensure its accuracy. A pre-UV sample valve. The UV system itself with the internal monitoring of the UV with dose of 1 monitor per lamp, with a temperature sensor on board for high temperature shutoff if needed. A post-UV sample valve. This is showing a relief valve to avoid any hydraulic issues. And the divert valve is the last piece of the system. And then we go into the swing for CIP. The next slide for simplicity shows basically how we would handle a surge tank. And the reason a surge tank is important is is with a surge tank, you can keep the unit powered or in forward flow at lower flow rates and then go to full flow without having to divert water until the dose and flow are balanced. And by keeping the unit powered and circulating at a low flow rate, you can avoid overheating the unit while keeping the unit energized. And by keeping the unit energized, you'll extend the bulb life without constantly cycling the lamps on and off. And of course, after a preset time, the light will turn off to save energy. So basically the same system. We start with CIP. We go through a pressure reducing valve, then basically on to the next required piece, which is really our flow control valve, into our meter, into our UV lamp, and then out of that into basically our next required piece at least is our divert valve. And then our divert valve in this case would send it to a balance tank, if you will. So we would reserve the water and basically recycle it until the system is needed. A system generally has about a 30% or can run at about 30% of its stated quality in forward flow. We have also designed, I haven't shown it, but basically a pasteurized equivalent water system that has a storage tank. Again, this is very useful when high rates of flow are needed for a short period of time. We can build a surge to balance the pasteurized equivalent water supply with the usage and keep the UV system basically sized for the average rather for an infrequent peak load. So an example of this might be when we are flushing multiple lines or multiple CIPs flushing simultaneously. And the last slide just shows a couple of models of a skidded system where the size can be kept relatively compact, and for providing a skidded system versus on-site construction time and cost can also be reduced. And now I believe we have our second survey question. So I'll give a moment or two to review and to choose a response, if you will. Okay, now I'll turn the presentation over to Dan Shaver for the specifics on how the aquarionics systems meet the requirements of the PMO.
All right, thanks, Dan. So based on what has been discussed earlier about the FDA's guidelines for creating pasteurized equivalent water within a dairy, I'm going to take you through some of the various equipment options that aquarionics can offer in order to help customers meet the specific UV requirements of the PMO. So we can basically offer assistance to customers in 3 different ways. And each of these ways has different levels of involvement from us, depending on the existing infrastructure and different technical capabilities of the customer. So aquarionics can offer a UV system as a standalone piece of equipment. That would be option number 1. This is the same way that we would provide standard equipment to many of our other industrial applications. Secondly, we can provide the UV system along with an integrated controller, and we'll discuss that in a little bit more detail, so that would be option number 2. And the final option would be, as Dan has discussed, working with a third party to provide a full turnkey solution to meet the requirements of the PMO. So UV as a standalone equipment, this is option number 1. So we have a full range of products available to meet end user performance requirements, but for the application that we've been talking about here as far as creating pasteurized equivalent water, we're going to be talking about the PureLine PQ system. And as Ken mentioned at the beginning, the PureLine PQ is part of our product family that is our third-party validated system. So this is the system that uses a medium pressure lamp technology. With the PQ validated system, we are able to achieve the minimum 120 millijoule dose requirement that Brian talked about in his section, and that's for suitable use for the PMO application. So the PQ products come with an automatic wiper system, and this helps to keep the quart seats clean from any fouling, and that could basically affect the system's ability to achieve the minimum dose. It also comes with 1 UV sensor per lamp, and that's been discussed about the importance of having 1 per lamp, as well as an external UVT or UV transmittance monitor, which you've heard of a number of times in this presentation. So again, I wanted to highlight that it's important to note the difference between measuring UV intensity and UV transmittance and why it's critical to have both. So while UV intensity is going to give you an indication of the overall lamp health and might provide indication of fouling issues. The UVT is your true water quality measurement. And given that changes in UVT are directly related to changes in the dose, it's very important that UVT is measured directly and not simply derived or assumed from changes in lamp intensity that could be taken from multiple sensors. It's important to note, too, the maintenance that comes with the system. So the maintenance of a UV system is generally pretty straightforward. Most of the tasks happen on a somewhat annual basis when the UV system has been running under normal operating conditions. These tasks include lamp replacement, sensor recalibration, quartz sleeve cleaning, and wiper ring replacement. While there is an automatic wiper on the PQ system, it's generally good practice to give the quartz sleeves a thorough cleaning. Usually when the lamps are being changed is a good time to do that, and those quartz sleeves can be changed approximately every 2 years. So there are several advantages to considering the PureLine PQ as a standalone product, but I want to make sure that some of the most important benefits are highlighted. So one of these benefits is the fact that it uses a medium pressure lamp. With medium pressure, Ken talked a bit about the differences between medium pressure and low pressure. And we use medium pressure often to accommodate for higher flow rates in a very compact footprint, maybe for installations where physical space is limited. So the PQ product line comes in various sizes depending on the customer requirement. However, the smaller footprint that we provide allows us to treat up to about 1,500 gallons per minute in a single UV system. Obviously, higher flow rates could be accommodated for using multiple systems if needed. As mentioned in a previous slide, our system does include a comprehensive monitoring package, so that includes both the UV intensity sensors and the UV transmittance analyzer, as both are required by the PMO. If you were to take a comparison of performance and efficiency between UV disinfection and conventional heat pasteurization of water, it shows immediate advantages for considering UV as a viable treatment option. So there are substantial energy savings available by implementing UV, and in some cases, we've actually seen that UV can consume up to about 95% less energy than conventional heat pasteurizers. So another benefit of using UV is the ability to have water available on demand and eliminate or at least reduce the need to store water for applications where UV would be suitable, and it could replace aging heat pasteurization equipment. So it's important to note that if a customer does choose this as option number one, that they still are required to supply the necessary communication and data collection tools in order to meet the PMO requirements. And that's what I'm going to talk about a little bit on the next slide here with option number 2. So our second equipment option would be able to provide the UV system as a standalone piece of equipment, so all the benefits of the last slide, but they'd also get the communication and data tools required. So they would have the benefit of the integrated Allen Bradley controller, which uses our intuitive touchscreen display. So the controller itself, as Brian mentioned, is very important because this was designed specifically for use in the PMO applications. It truly is a unique product offering in the industry that gives our customers all the functionality and reporting required by the PMO without being bound by any proprietary design or communications. So the UV Touch system, as we call it, is an open source platform. It's designed to be fully compatible with existing plant communications, which makes the integration of the equipment very straightforward. As you can see on the screenshot here, all of the necessary monitoring and performance parameters are available in an easy-to-read format and able to access different reports. So customers will have a real-time indication of UV transmittance, UV dose, temperature, flow rate, any alerts of action taken with a divert valve, and access to trending reports and specific details of alarms that have occurred. So the PMO recording software is built into the control system to allow for a very simple compliance report when it comes to providing any kind of performance information that a regulator might ask for. So on these sample reports that you see on the screen on the left, you see a report that generates flow rate and UVT trending reports. And these are just available at the touch of a button on that previous screen. On the right, you see a compliance report. This easily shows alarms from parameters that were outside of an acceptable operating range, as well as the action that was taken. So in this case, if you look, there's cases where a scenario where the UV transmittance dropped below an acceptable range, or the dose dropped below an acceptable range. So not only does it show the alarm that it occurred, but more importantly, it shows the action that was taken. In this case, a valve was closed. So option number 3, this final option would be, as Stan's already talked about in detail, would be to work with one of our third-party sanitary process distributors to provide a full turnkey solution that meets all the UV requirements of the PMO. So I'm not going to spend a lot of time on this option, as it's already been covered earlier in the presentation. Stan's done an excellent job indicating what a complete solution would look like and how our sanitary process distributors can get involved in the solution. So with this option, the customer would get all the benefits of the UV, the integrated controller, and they would have all those additional flow, diversion, and shutoff valves that are required as part of the PMO. So with that, we've come to the next survey question. So very simply here, we want to know from you if you would like to discuss the use of UV at your facility or a future project in more detail. And after the survey question has been answered, I'm going to put up some contact information for you that you can use for the future. All right, thanks for your answers, and that concludes the slide portion of our webinar. And before I go into the Q&A, here's some contact information. So the contact for myself and for Brian. If there's anything that we could do in the future to help you answer your questions or provide more detail, feel free to reach out to us. And just wanted to take the time on behalf of our team. Thank you for taking part of our webinar today. I hope you found it useful, and we look forward to speaking with you in the future. So I'm going to turn it back over and get into the Q&A portion of the webinar.
Thank you, Dan. I appreciate that. A few questions have come in. I don't know if we'll have a chance to get to all of them, but again, we will follow up afterwards with any questions we're not able to answer. So I'll just read through. I'll just read through a couple of the questions and either answer them myself or pass them off to other presenters. So a question has come in. Is it compulsory to replace the quartz glass in 12 months? So I'll speak specific to Aquionix. I would say that every manufacturer may have a different recommendation. In this case, the recommendation that Aquionix makes is that quartz should be replaced every 2 years. And the reason for that is over time, quartz can solarize and become brittle. And the last thing anybody wants is for a quartz sleeve to break within a process. It's a very rare occurrence to happen, but we would recommend that quartz sleeves be replaced every 2 years to ensure that a breakage doesn't happen. Another question that's come in, are parts stocked in the U.S.? Again, a specific question for Aquionix, yes. So our facility is based in Erlanger, Kentucky. All parts are stocked there, plus systems are stocked there. So there are very few things that we are not able to support on an everyday basis. So we have a question. Let me get to it here. So we have a question. What is the minimum water quality required for UV? And Brian, if you don't mind, can you take that question?
Yep, sure. So, that's going to depend on each specific UV system. So some are going to be able to handle lower water quality than others. The primary value that we look for as a UV manufacturer is that UV transmittance that we mentioned several times throughout the presentation. Typically for RO permeate and high quality water, you are talking above 95%, but we have seen some applications for cow water reuse where you get more variability and lower UV transmittance levels, below 90 typically. So it's important to measure that and maybe capture several measurements to ensure that you really are looking at worst case scenario. Other things to keep in mind, for example, if it's a well water source that you're trying to treat for pasteurized equivalent water, iron and manganese in particular are two constituents that you really want to understand how much is there in that water. So, for example, iron, you can only have about 0.3 milligrams per liter as a maximum. Manganese is 0.05 milligrams per liter as a maximum. This is because those constituents in particular will bond to the quartz sleeve, and that'll prevent the UV light from penetrating through the sleeve and therefore properly inactivating the organism. So what we really want to look at is iron, manganese, UV transmittance, total suspended solids perhaps, just depends on the application. But UV transmittance usually gives us a good starting point for us to determine if some of those other issues might exist.
Thank you, Brian. So we've got time for one more question here, and the next one that came in was, can Aquionix share third-party validation envelope information? And I'll address that. So the answer is yes. So obviously, third-party validation information is specific to each UV manufacturer, and it's not something necessarily any UV manufacturer wants floating around in the industry. It's the secret formula, so to speak. It's the validation envelope. So anytime that information is shared, whether it be by Aquionix or with another manufacturer, there'd be an expectation of confidentiality. Typically, a non-disclosure agreement is asked for, but UV manufacturers are used to providing that. It's something that we're expected to provide. So yes, the answer is yes. We can supply that information, but again, it would come with a non-disclosure agreement. So we have reached the time limit for this presentation, and there are some other questions that are rolling in, and we will make sure that answers are delivered to each one of those questions. We want to thank everybody for their time and logging in. We'd like to thank Stan, our guest speaker, and his time given to this presentation, also Brian and Dan. And thanks to the audience. We greatly appreciate you taking the time to listen to more information about PMO and UV. Everybody have a great day, and thank you.